Mark, you are on, you and your dog.
Yeah, this is Pinky. It's Pinky and the Brain. Pinky dead. Okay. So here at Falcon Space, we've been working on a couple projects, namely Alzaphon, and we're also excited to try the particle impulse experiment again. And we just learned some new information earlier today about the pressure necessary for that experiment. So I'm excited to try that. We got the big vacuum chamber hooked up behind me to that vacuum pump, so that's working great. I also got some pyrolytic graphite over here that we're thinking of trying another variation of the particle impulse experiment using the pyrolytic graphite, because that's like damn near a superconductor at room temperature. You can see this right over here. It's actually floating. It's kind of hard to see on the video, but you can hear that clicking. I'm pushing it down on the magnet and it's rising back up. So that is basically room temperature superconductor, diamagnetism, whatever's going on over there. So we're going to do like a bilayer of that as well. And we'll use the vacuum chamber over there for the impulse experiment. What's going on with Alzaphon? Well, we had some trouble with the copper pieces that were cut for the waveguide chamber were slightly too large. They wouldn't fit inside the magnet. So I got some new pieces cut. They just arrived at the lab last night. I need to remove them from their substrate. So that's a solvent process because they're like glued down. And then I'll be able to start tuning the chamber. We're using graphite. This was Tanya's idea to put a piece of graphite in there and figure out when the chamber is in tune. I also got cross guides for the X-band system, so we'll be able to do it both in X-band and in C-band inside the massive magnet over there. I actually just measured the magnet, the electromagnet, to see if it will fit inside the Faraday cage, and it does it by ½ an inch. So we're gonna have to like stretch the door wide open to get that thing in there so that we don't get all these headaches like last time. But we're very excited to have, what's his name? I hope he didn't leave yet. Brian Sinclair over here. And Jeremiah shared a video with me earlier of Brian's. And Mike, you're going to like this as well. It's a very similar concept to what you were working on. Let me see if I can do this. Share screen. That should be working. Is it working? Tim, give me a thumbs up. You see it? Okay, good. So I'm just going to start this. And this is Brian's video. Wow. What is going on there is it's pretty amazing. Here's another video from Brian, and we'll get into
Hello everyone, Brian here. All right, we've got the Pi 4.8. It's the counterclockwise or CCW rotating unit, as you can see. Okay, this is just a quick bench test, just make sure that we have the propulsion set correctly. Both with and without the SDC operating, this unit does self-propel. It definitely pulls forward very nicely, even at incredibly low speeds. So I want to show a quick demo on this right now. The switch is off, so the SDC is not operating. Okay, going forward, let's slow it down just a little bit. As you see, I've had to hold on to it so it doesn't take off on me. I've just got this sitting on some pieces of pipe because it's not really ready to be put with the other unit yet. So now, even without the speed control, speed differential control operating, yes, DC. Now with it, it's pretty dramatic. So higher the speed, the better it seems to run. The bench is level. I do also, I've had a couple of sockets sitting in front of it just to watch it push the sockets. There you go. We'll push those right across the workbench too. So it's got more power than it needs to move, which is great. I'm very pleased with these stops. I'm very pleased with the weights. I'm pleased with the fact that they're dead blow in design. And I'm very pleased also with these guides that are mounted right to the weights. So they actually cannot leave the center until after they normally would. It just holds them there a little bit longer. It helps with the timing of the whole thing. So that's all I've got for right now. I appreciate everybody watching. There'll be more to come really soon.
Okay, so I'm going to stop the share. So that was actually Brian Sinclair's system, and we were talking about
I got a comment to make. Both of those demos are really replications, exact replications of Roy Thornson's inertial impulse drive. We actually built them with some undergraduate students years ago. We published the results. The impact to the axle is the key to transferring momentum. And that was hard to analyze mechanical engineering wise, but that is exactly what you see in Roy Thornson's patents and also in his video. So credit should be given to Thornson, because even as Boeing looked at it and Jamie Childress evaluated it, the impact was so onerous that nobody wanted to commercialize that invention. But it looks good. It provides thrust and it goes up a 10-degree incline. So I give credit to Roy Thornson for that invention. In case you don't have the patents, I can give you the patent numbers.
Well, thanks, Tom. Thanks, Tom.
You're welcome.
Yeah. Well, let me see, Mark.
I'd like the patent numbers. Just throwing that out. If you either want to put them in the chat or something.
Yeah,
else.
absolutely.
Yeah, and yeah. So, Mark, I mean, we have Brian with us. Could Brian describe these a little bit, what he's built and all that stuff?
Yeah, go ahead, Brian.
All right, thanks for having me on. Yes, I do want to give all the credit in the world to Roy Thornson. He's the one that came up with the entire planetary gear set.
Right.
Without an orbital gear, which is great. No outside gear.
Right.
Just a single center sun gear and then planet gears orbiting it.
Yep.
Yes, a lot of the forward momentum comes from impacting with the center pin.
Mm-hmm.
Roy had said that you cannot allow it to pass the center pin. Well, actually stopping before the center pin is a little better even. With this design, the outer stops are what Roy in his patent called the outer planet traps. He was using those to hold the planet weights back and not allow them to flip out until later on, which is part of what I'm doing with the extended guides that are on the weights themselves.
Yeah.
The outer stops are built into the planet gears, and that has made a dramatic improvement in how this works. That and the fact that thoroughly by accident, I found exactly where the speed needs to increase every moment in the revolution. And that was because of that very first set that we saw there, the one that was unpainted with 4 wheels turning. that was running on a belt that could slip. And if the belt was allowed to slip during the moments of heavy load, the whole device would stop moving. So what I've done is I've put in a positive drive with the roller chain, and I've also put in a speed differential control. Basically, it just bumps the speed up ever so slightly in those moments of high load. Reversing the slowdown, it actually speeds it up. So there's been a few changes. It's been great. I want to give, like I said, I do want to give all the credit in the world to Roy. He did a great job with it. It's unfortunate that he's passed at this point. It's unfortunate that he never really got the recognition he deserved for it. So we're kind of putting it forward here. I didn't want to mar any kind of memory by calling it the Ezekiel like he did. So PI, it's a pulsed inertial engine. It's kind of a generic term, but it works.
Well, now if I could jump in and ask real quick, for me, the Thornson canoe actually was really amazing. And that's one of the few videos that I've looked at, and that for me, that was inspiring. And your thing as well, because it's heavy and it's still moving, right? It's got mass to it. So, but so with what Tom was saying about it's impacting the pin, is it just the mechanical vibration that stopped Boeing from looking at it further? What were they worried about, damaging the equipment, or?
I'm really not privy to what happened as to why his four-wheeled high-speed unit never came to be. I saw videos of it. I've got the video of a lot of his early work, and where he showed it, but he said, well, we don't have it working. He was expecting it to be running at 3,000 to 4,000 RPMs, I understand.
Yeah.
I do wonder if his increased speed had a problem. This does seem to have an area where it's almost a harmonic, where the speed can outrun the efficiency of the design. And if you overspeed it, you start losing propulsion rather than gaining more.
Yeah, I wondered. I thought the canoe was really interesting too. I thought that it would be interesting to continue that, right, with lightweight floating vehicles, and then you give a really good demo with that.
Absolutely, I would love to get it in a canoe and see how that would work out. This is version 4.8. Version 1 was a two-wheel design. In the videos on YouTube, it would be the one that's green, or has green weights. It worked. It didn't work great, but it worked. It worked as well as the four-wheel design that with no paint on it. Okay, so to me that was a version 1. I did fix the problem with the belt slipping by using a timing belt. Then I went on to version 2. Version 2 was a double stacked wheel. So one wheel was on top of the other, and I was using 4 much heavier weights. That produced a lot more propulsion. Both of those were mounted in the back of a vehicle and driven down the road so that engine load on a test track could be measured. The first one would eliminate 6% of the engine load, and the Pi 2 would do up to 13% of the engine load. So there's an obvious application for that as a hybrid design.
Yeah.
There is a difference in the way the timing would be set up between wheels and between weights. What works better for a hybrid design doesn't work as well as a self-propelled design, which I found kind of odd to begin with, but now that we're studying it a little bit more, it's starting to make sense, and I think we'll have some definitive answers for that here shortly.
It's interesting. Yeah.
Does anyone want to see the actual historical canoe test that we were talking about from Roy Thornson?
Yeah, Tom, if you'd be open to putting it up.
It's about a 3-minute segment, and it has this bearded expert summarizing it at the very end too. Okay, here we go.
The force of inertia is known in mechanics.
It's from free
But
energy
until
race to
recently,
0 point.
It had been considered too weak and difficult to harness for propulsion.
It's on YouTube.
According to some theorists, like Hal Puthoff, inertia, like gravity, is what occurs when we try to accelerate an object against the 0 point fluctuations in the vacuum. We run into resistance.
There it is.
Canadian inventor Thornson has developed an inertial impulse propulsion engine which overcomes that resistance using centrifugal force. It pushes against nothing and emits no exhaust, but it's been calculated to be 20 times more efficient than a jet engine. Here, the Thornson inertial propulsion drive powers a canoe in a swimming pool.
The canoe is symmetrical. That's why we use it.
Which is housed in a box, never contacts the water.
Toby Groats looking at it.
In the pendulum test, unidirectional force is being generated to keep the pendulum to one side. Whether or not we can demonstrate, as I have, with engineering analysis and models that will climb and incline, will pass this pendulum test, and they would stay on one side of the pendulum consistently, and even power a canoe in a swimming pool. Commercialization of that device is still a very difficult road, and we see that in many inventions. But what I like to emphasize is my F/P measurement of that is literally 20 times better than the jet engine. A jet engine, typically a commercial jet engine, the DC-9, I think is the one that I analyzed, has about 0.016 newtons per watt. And this is in the metric system. Now, when we look at Thornson, he's able to achieve 0.32 newtons per watt, literally 20 times better than the jet engine. Roy Thornson is developing refinements to his system to increase its performance. Unfortunately, like many inventors, even with a U.S. patent in hand, he's yet to find sufficient investment capital to bring his motor to the market.
Oh, that's about it.
Oh, thanks, Tom.
Welcome.
Tom Valone with a beard. I've never seen that before. Took a moment to recognize you. I was like, wow, wow.
That is to teach
Is there
college.
a version of the of this drive using mercury, like spinning around in a tube of some sort?
Not that I know.
Not that I'm aware of.
I thought there was a shake one with mercury. Yes, there was. I don't remember. I remember seeing something about that. It was, what do they call it? Like a liquid inertial propulsion or something.
Me and Jeremiah were theorizing what would happen if you spun mercury in the shape of a capital D, half circle and then straight across. Would that create
Not just a capital D, but specifically it needs to be starting out slowly in a wide tube. It needs to be pushed into a narrow so that it accelerates, it gains momentum, and then it needs to change angle quickly so that it's at a high speed when it's exerting force on one side, and it's slowed down by effectively returning in that path through a expanding tube that changes velocity back down.
You could test that with water and get an effect.
Right, you should be able to test it.
With
I think
water.
that's what he was really asking is, yeah, you got to change the diameters too, but to get an opinion on that idea is what we would like to hear.
It's very possible. If you look at the shape of the movement of the weights, the actual center of mass of the weights is moving in what would look like an upside down heart, with one lump of the heart deformed. So that seems to be kind of a constant. I've worked with a couple of people overseas that have worked with similar designs, and they've found that shape also is closest to what they'd already built. So it's something to be considered, to watch what shape it's actually traveling
But now, Brian, you were saying if you put this thing on like a bigger motor and just spun it a heck of a lot faster, you think you might run into issues because there's some speed dependent aspects to it, right?
I do, and what's really weird about that, to me, I'm not a physicist, and the math is slightly above my head. But what is very interesting to me is that it is speed dependent. If you spin it faster than its design allows, I'm sure that with a smaller gear, with a smaller wheel, everything being a little bit smaller in diameter, higher speeds would be possible. Bigger, I'm pretty sure would require lower speeds. Speeding it up in the middle of the process with that speed differential control made a huge difference. But still, there is a point where it would outrun. And it would be with the weights that I'm using right now, they're 2 kilo. They're pretty heavy. So if you were to spin those pretty fast, you'd have to have a heck of a lot of pin and axle and everything to hold them in place. What I found was extremely interesting, and I didn't get a chance to fully test this whole thing. This is going to be part of the testing that's going to happen in the next round with the Pi 4.8, is that the faster the vehicle was driving down the road, the more power it was producing forward and the less reversion there was. So that's another thing to be considered. It's counterintuitive. You would think that it would outrun its ability to propel, but it seemed to be doing exactly the opposite.
One thing I wondered, it just out of curiosity, is, and also this would help keep it maybe at lower speeds that'd be more mechanically manageable. You know how in an engine, this was, and again, when I saw the Thornson video, this kind of been floating around in my head. In an engine, you have multiple cylinders that are out of phase, right? What if you had multiple of these, almost like a V8, where instead of having to run the whole thing faster, what if you had like a horizontal stack of cylinders and they were just, yeah.
That is an incredibly good possibility. That was not easy to do if everything was synchronized properly. Because they would start to cancel one another out.
Oh,
a lot of that problem has been overcome with the adjustable outer weight stops and using a dead blow weight design. Those weights are hollow and filled with steel shot. So when they impact something, the impact lasts 2 to 3 times longer than simply coming up against and giving it a quick shot of something. So it's almost like a storage of inertial energy, and it releases it a little slower to keep that momentum going. Yeah, the whole thing about it, producing more and more power the faster it goes. If you bring it all the way to a stop, put it on a long enough surface where you can bring it to a stop with your hand and just allow it to keep moving slightly, the faster you allow it to move, the more it tries to pull your fingers. So even that is kind of proving out that point. It's almost like an inertial Doppler effect, where the power is out in front of it, and what's behind it is nowhere near as important. So those are all things that are on the ticket to be explored and documented properly with this next round of testing.
Yeah, well, it's amazing work. Thank you for sharing that.
Oh, you're welcome. I appreciate the chance to come on and show it.
Yeah, absolutely.
Ryan,
Yes.
question. Do you have any like AutoCAD or SketchUp diagrams of the gear setup? Because we could technically 3D print this, and if it works, put it up on Thingiverse and everyone can build one with a 3D printer.
Absolutely. I don't have it on AutoCAD, but a friend of mine does. I think he's got the whole thing on CAD. If he does, I'll be glad to send it over to you. You can do whatever. Like I say, I want to keep this entirely open source and completely public. Number one, it prevents the machine from going missing. You know what I mean? Certain things that have worked that suddenly don't exist anymore. So it prevents it from going missing. It prevents anyone from threatening me to make it go missing. So there we go. Now it's out there. Everybody's seen it. We all know it works. Let's build them. And, you know, people have asked me, well, hey, you know, if you wanted to make a business out of this someday, how are you going to do that? It's like, you know how many car manufacturers there are? You know how many engine manufacturers there are? My goodness, you know what? There are tons of billions of billions of dollars to be made if this was actually utilized in motor vehicles. Come on, you know.
I'm totally with you on that. Like this entire field of what we're trying to open up is multi-trillion dollars. There's
absolutely
room for everyone, and what we're working on right now is probably not going to make it commercial anyways. These are stepping stones to get to a working longevity product. You know, we're going to work them to hell until they break, figure out what broke, change that part, you know, make it even better. It's going to be several years away until we get
right. That was part of what the 2.0 was all about. That got actually pushed past its mechanical limits out on the road, and that's where we got the maximum of 13%, was just before it started losing gears and pieces. It would stabilize at 11.5 to 12%. That was right at its mechanical limit, not surpassing what it was built to do. So
what's the biggest stress point?
The biggest stress point is actually the teeth on the gears. I've worn gears out. I've got people emailing me and messaging me, man, you've overbuilt this thing. Oh my goodness. Dude, you want to see all my busted gears? I've got lots and lots of no teeth gears to show you. That seems to be the biggest point of stress, is on the gears themselves, because the gears are taking the lash in both directions.
What kind of metal are you using for it then?
Let me start by saying I wanted these things to be as cheap as possible. I wanted every mechanic with a welder and a chop saw to be able to build one. All right. So the gears are actually made out of sheet metal idler pulleys with a ball bearing. The Planet gears are number 40 27 tooth roller chain sprockets welded to those pulleys, and the center gear is two of those sprockets with 5/16 rod welded in between each one of in place of where the rollers of a chain would go. And that actually, I kind of like doing it that way, because I was able to move the gears up and move the gears down. I had some designs where they were hitting each other as they came around, and I was able to stagger them up and down that way. So, I mean, they're not made out of anything special or anything particular. A friend of mine in Japan has built several units. His first name is Tokyo. I wouldn't try to bastardize his last name, because I know I wouldn't get it right. He's built some designs using some gearing that were offset, so that it would actually change the speed of the rotation, because the gears were actually changing diameter. And he built some awesome machinery, and it exploded his gears. And those were not homemade gears. Those were expensive machine shop gears. So yeah, you know what? Cheap gears are fine with me. I'll burn them up all day long and throw them away and build new ones.
Well, surely there's some way to get like a hardened metal so that you're not smashing up the gears.
Well, yes, you can get steel gears with hardened teeth, probably with a helical cut, so you'd have a right gear and a left gear that would have to mesh together. That would also be a little quieter. It produces more surface area for the teeth to mesh. You can come up to like a 29 degree contact mesh for the gears. So I mean, it's possible to do gears like that are very capable of handling a lot of heavy loads. Like I said, I wanted to build this thing cheap enough so that everybody and anybody with a welder and a chop saw could actually just put one together. And that's kind of where we're at.
Here's my offer to people that want to build it. The Inertial Impulse report from Roy Thornson. It's on Amazon, but you have to get the title right. Inertial Impulse Engine of Roy Thornson. And or you can look under my name and find all the reports. but this is only $5. It has everything Roy Thornson sent me, including all the drawings. So you can build one yourself and then multiply it like Brian did to have several of them. But you'll find every single drawing that you need in here from the boss who invented it.
It is a terrific book. I've got the book. It's an outstanding read. There's a lot of outstanding information in that. Very nice, technical, and well presented.
Yeah.
I also have a manual that I put out if anybody was interested
Yeah.
in building.
That'd be nice. Yeah.
Brian, do you have links to that?
Yes. Just go to Sinclair Tech, STCLAIRTECH.tech. And that will link you to my blog where I put as much information as I can stand to type in there. And it also links you to where you can purchase that manual. That's the only thing I'm charging anything for. Everything else is free.
Okay, so here it is, sinclairtech.tech. So what I'm going to do is I'm going to make a note and I will put this in the write-up for the conference too. And I'll try and get Tom's stuff in. Tom's dropped a few books as well. And that way people have access to all of it. So
absolutely.
Something amazing just happened here on APEC. So in the chat, HT Alvarez just posted that the patent that we were basing that idea on to do the D shape, he actually put in the patent application for that, and it does not work. So
well, back to the upside down heart, huh?
Yeah, maybe we'll try the upside down heart shape. But you said there was a lump on one side.
Right. If you were to draw a perfect heart on a piece of paper, and one of the two lumps you flattened out a little bit, that would be, or put a dent in it, or whatever. You've got to deform it, make it smaller, and that is the form that works. That can be messed with depending on what kind of weight you use and what the size is, and those things can all change a little bit. But that is the base.
Can you maybe give us a diagram like that, or maybe take like a picture of the device spinning, or video of the device spinning, so we could see also its speed, where it accelerates? Because we can put the acceleration point for the linear motor at the point where it needs to accelerate, for maximum effect.
That diagram is in the report. That's Roy Thornson.
There is a diagram. Yes, that diagram is in the reports.
Oh, perfect. I just ordered it, by the way. Thanks, Tom.
It would look a lot like that.
Yeah, upside down.
But it would be upside down.
Right.
Now,
so, I mean, yeah, it's all in the reports. It's all there. It's like I said, there's terrific, outstanding information in that report. So yeah, by all means.
I guess I should ask, since we have Harold Tavares with this, I'm not sure what his bandwidth is. Mark, do you want to try and talk about the D-shaped thing with Harold, or if
I mean, he just told us that it doesn't. I think it was Alvarez. Was that?
Yeah.
Harold actually has a lot of patent applications. He's gone through quite a few ideas and been fairly busy with this concept. I'd kind of like to hear more from him about what he's come up with over the years, and if he's found anything that he does think will work and why.
Yeah. Well, here
the D-shape. Sorry.
Oh.
Can I just interject?
Yeah, go for it, Wayne.
Yeah, the D-shape thing won't work because it's like, you understand dynamics, right? Because you're changing the direction of velocity, like it's all going to cancel out, like around the whole circuit. I thought of this a few years ago, and if you just understand the dynamics, it's not going to work. And also, I was wondering about that the gear machine there, if that's been tested in a friction-free situation, because I've done quite a bit of work with pendulums and stuff, and I've been able to move things across a flat surface, but it boiled down to, for what I made, it boiled down to it being a difference in friction from the way the masses move on one side compared to the other. So you get kind of a slip and stick situation.
Right.
I can answer that actually, just in defense of Thornton. Basically, the rowboat test would fulfill your friction idea. And in a rowboat, you got a flat end that enables the rebound to push against the water. But he's using a canoe that's symmetric. So you really don't get very much frictional response, any different than when you're going forward. So that's why the canoe was the special vehicle to use in the water. But when you actually suspend it from a pendulum, there's probably the most closest you can get to a frictionless surface. However, I can give a plug for Mike Gamble, because his next plan is to use an air table, air cushion table, so that like a hockey, air hockey play table, and essentially you'll fulfill your requirement that a lot of people ask for, a frictionless surface, to see if it really does.
Yeah, I've had the Pi. I've had the Pi capable of swinging on a pendulum, and it will. You can make it work like that every time. The problem I have with pendulum tests is because we're moving weights back and forth from the front to the back of the pendulum. It's oscillating already, and if we put a bias of weight at one side or the other, it's going to show that it's working even if it doesn't. It's just like having the rowboat test with the flat surface at the back. You can make anything that oscillates scoot across the water.
Right.
Absolutely.
There's a similar problem with the air hockey table. If the center of because if it's not balanced properly and it's tilted slightly to one side, the air is going to fall on one side and move it in that direction.
Right. You did definitely have to make sure it's level.
What I really like is that I can put more and more and more weight in front of this and watch it push it across the table. You know, the table doesn't have to be perfectly level. If it goes up a little bit, as long as it doesn't go, angle up far enough to roll backward. That angle doesn't hurt it. So 2, 3, 4 degrees is fine. And I've had it pushing 12, 14 pounds across the table. I mean, granted, I didn't measure the amount of force that it took to move those weights, but we're pushing, round chunks of steel that were sitting on a painted surface, pushing them across the table. There's certainly a lot more.
Roy went up a 10-degree incline. Right. Well, credit to Roy Thornson once more.
Oh, absolutely. The big thing with that is because of the slow oscillation that is keeping it from rolling back. And that's the big problem with climbing an incline with the slow oscillation unit. With a faster speed, oh yeah, absolutely. And with a faster speed, it would work even better. Absolutely.
Yeah.
Go for it.
I think it's really exciting. Brian, I think I thank you for sharing this. I think what you're doing is really exciting.
Brian, I have a suggestion for you. Maybe get like a thick rubber band, kind of long, and attach that to a force measurement transducer. This way, it will have the ability to move around a little bit from all the motion, and you'll end up with like a net averaged force.
Right. I just received a force meter the other day, so I honestly didn't have one in the shop.
Use the rubber band.
Right. I just started messing with it. Holding it still doesn't work, so obviously the rubber band thing is a lot better. I have put an accelerometer program on a phone and fastened the phone to the unit. And I've got a couple of waveforms that I've saved, but it's pretty dirty. It is what it is. That's just this test unit, and it's only half of the unit. So I'm kind of looking forward to getting the whole thing put together and then really seeing what the tests show. I don't know if anybody can see that or not. That is the waveforms of the accelerometer testing. Now, that just happens to be 2 of them that I saved. Yes, there are spikes going in the other direction. But it's such a dirty waveform. There's going to be spikes all over the place. The big thing was that it had a bias below the 0 point, and below the 0 point was the forward direction. So we're headed in the right way with this thing. So it's just testing it out, getting it to be as efficient as possible, and then moving on to the next design.
Have you seen Steve Hampton's work? he's been building these for several years, and his waveform is not much different than yours.
Right. His waveform isn't a whole lot different than that. I've seen that, and I was kind of comparing it to that, but I hadn't gotten quite that far to even mention it yet.
Yeah, I built the accelerometer for his device to test it out. So
Sure. No, that's great. I cheaped out and just put a program on an Android phone and taped the Android phone to the unit.
yeah, we did that once.
The phones don't last long.
Okay, we also have another update from the lab. There is going to be a news article coming out about us this coming week on the debrief. And also we got some volunteer help here at the lab and managed to organize all of the, we have over 100 boxes over there organized. So we're getting a lot more organized and putting things together. I guess all of you guys kind of try to do that every once in a while. And hopefully we'll have Jeremiah down here sometime so we can do some of these, some of these experiments require 2 people. Yeah, we're pushing forward with everything.
Well, thanks, Mark. I should mention, Ed dropped a link in there. Let me see, the Milkovich 2-stage amplifier, the mechanical oscillator. He dropped that into chat, and then Will dropped one in there too. I haven't looked at Will's yet. So.
Yeah, if you go to my YouTube channel or BitChute channel, either one, you'll find that I've got some of those videos on there as well.
Ah, cool. Yeah, this is really exciting. Brian, thank you for sharing that with us. And Mark, thanks for showing the videos. So did you have anything else, or should we go to open discussion now?
Go to open discussion. I mean, I pretty much gave the update from the lab, but
okay. Well, yeah. So I'll call it then. Open discussion for today. It's a free for all. Everybody can unmute themselves, and
yeah, just don't all talk at once.
Well, first off, huge thank you to Brian for an impromptu, completely out of nowhere, and amazing discussion that followed from the showing of those videos.
Well,
so thank you so much. That was awesome.
Yeah, and to Frank Ferguson as well. And I owe you guys an apology for playing with the schedule a little bit too much. Tony went short, and then I didn't know, Paul Lavalette had mentioned Frank, and I didn't think he'd respond today. And then next thing I know, he was in the conference. I said, well, he's here, let's get him on. So I should apologize for disrupting our schedule, but
yeah, it was totally messed up. And the Dean drive, we missed the Dean drive completely.
That's my fault for misreading his
terrible.
emails.
I feel so deprived.
I just got too enthusiastic. I got too enthusiastic about his.
Everyone
save it for next week.
Mike is all upset too.
Well,
everyone get a lot of refunds.
And Gary Stephenson has something too. I'm not even sure if Gary is with us anymore. I know he popped in. Nope, I think Gary bailed out. Gary Stephenson has something for May 15th. So